Okay, so today what we're going to do is we're going to finish up module 7.3. And module 7.3 also has instructions for the group activity. You should have gotten an email. If you didn't, I had one come back. And so I'm not sure why, but if you didn't get the email, go ahead and go to Canvas and download it there. Okay, the group activity is all about telling the difference between SN1, SN2, E1, and E2. Okay, so this is the thing that you really kind of got to get straight in your head. Once you get it straight in your head, you'll understand and say, oh, that makes sense. However, it looks like it's overly complicated and it looks like it's hard to do, but it's not. And I'm going to show you a step-by-step method for figuring out exactly how to figure out what kind of mechanism it is and what the products will be and what the major products will be. So the activity is all about going through this process, learning this process of what to look for, making an assessment of which mechanism it's going to be. Once you know which mechanism it's going to be, you'll know which of the products will be there and which will be major. Okay, so that's the whole focus of today's lecture. So let me go ahead and share my screen. First of all, does anybody have any questions? Okay. Okay. Remember, our exam starts at exactly 8 a.m. on Friday morning. I'm sorry, Thursday. Don't come to Zoom. Go directly to Top Hat. You should already be assigned an exam A or exam B. I will monitor my email the whole time. And so if you have trouble getting in, go ahead and email me. We'll try to figure out how to get it. I think all of us have gotten into it lately. I've heard a couple of people having computer issues, but we've been able to figure it out. So just go ahead and email me. We'll get you into the exam. No stress. We'll just go ahead and take our multi-choice. It's about 30 questions, multiple choice. So it shouldn't take you the whole time, but you will be there. If you do have ODS accommodations, you do get time and a half, and that will be already tacked in there. Top Hat added a really cool button called accommodations. And so each of the people who get them every single time. So I think that's a really good feature that they've added. All right, any questions about the exam?
I have one.
Yes.
The chapter 7 homework, there's a bunch of stuff in there about alkynes that I don't remember us going over in class. Is that stuff going to be on the test too?
No, the alkyne is going to be separate.
Okay.
I'm going to do the alkyne separate. The exam will be on Top Hat over Proctorio, yes.
Wait, so the exam is just going to be over SN1, SN2, E1, and E2?
No, chapters 1 through 7.
Oh, 1 through 7. Okay, got it.
With a focus on 5 through 7, because we already had a test on 1 through 4. But that is all fundamental knowledge we'll need for chapters 5 through 7. Okay, so it's focusing on 5 through 7, but it definitely has some 1 through 4 in it.
Okay, thank you.
All right, let me go ahead and share my screen. Okay, see that I'm going to move my gallery view up over here. All right. Oh, I'm not plugged in, that's why. There we go. All right. So where we left off last time is we were talking about different kinds of bases, and we had 2 kinds of bases to play with. We have our small bases that can act as nucleophiles or as bases. So there's always a competition there, specifically for SN2 and E2. Okay, but we know that we can change that product ratio based on the temperature of the reaction or the structure of the material, for example, primary, secondary, tertiary. These were the big bases. They are so big, they cannot act as nucleophiles. So we completely take out the SN2 reaction unless it's a methyl group. And for all other things, primary, secondary, and tertiary, they predominantly do elimination reactions, predominantly E2. Okay, so that's what we were talking about last time, and the fact that they're such strong bases, but they're too big to get close enough to start forming that bond through an SN2 mechanism, ergo, they always go the E2 route. Okay. So in reviewing this is where we need to get things straight in our head. okay? We talked about the difference between nucleophilicity and basicity. Remember, nucleophilicity is a kinetic reaction. How fast can I form that sigma bond? Basicity is about equilibrium. Where is the weakest base? Okay, so one is about kinetics, one is about thermodynamics. Okay, so we have them and we need to make sure that we have them different in our heads and we know exactly which is which. Okay, so polarizable bases or weak bases are good nucleophiles and mainly produce SN2 products. Okay, think about that. Iodine and bromine, those are really strong acids. So that makes them really weak bases. We have charges on sulfur. We have neutral sulfur, and we have this azide ion, the N3 minus. Okay, so because they are polarizable, the sulfurs are quite large, and we have the halogens being quite large. They mainly produce SN2 products that will typically be your major product if that's the only nucleophile found in the system. Okay, now, when we talk about strong bases that are small, like hydroxide and methoxide, ethoxide, small straight chain alcohols, we now have a strong base, but it's still a good nucleophile because it's small. Now, that means we're going to have a competition between SN2 and E2, okay? Because it's a strong base, but it's small enough to do the SN2 reaction. Okay, so we're going to have a mixture of those, okay? Now, for the bigger, bulkier bases, they cannot do that SN2. They're too big to get in there to start forming that sigma bond. So they preferentially form the E2 product. Okay. And you have to remember certain strong bases like this also try to form the Hoffman product. The Hoffman product is the less substituted one because of the bulkiness. Okay. So we need to think about the actual stereochemistry of our final product as well. Okay, now, once we get to things that are not good nucleophiles and are not good bases, they have to wait around for a carbocation. So we think neutral water, neutral alcohols. Notice the sulfurs are big and fluffy and polarizable and are good nucleophiles. The oxygens are not as polarizable and therefore in their neutral state, they are poor nucleophiles and poor bases. They must wait around for that carbocation, which means we're going to be in a competition between SN1 and E1. So the alcohol or the water is going to come in and interact with that carbocation, either in a substitution reaction or a beta elimination reaction, and you'll always get both products. So it's not very helpful to do, but we can trick it to do some certain things. All right, so questions on this? Okay. So the next chart is a table. I think this table is going to help you kind of organize everything, but you have to look at it, you know, piece by piece. Don't just say, ooh, pretty table. Okay. So on the top here, we have strong unhindered bases are also good nucleophiles. Okay. So strong unhindered bases are good nucleophiles. Therefore, you can get SN1 or, I'm sorry, SN2. Why am I getting texts on my iPad here? Okay. Okay. Strong unhindered bases, because they're small, they're strong bases, and they're good nucleophiles. Okay. So we have a competition between our elimination reactions or our substitution reactions depending on the substrate. Okay. Our big bulky bases now cannot act as nucleophiles. We cannot get it in there to start forming that sigma bond. So we predominantly do elimination reactions. Okay. When we have our weak bases, but we have a polarizable negative charge, we now have good nucleophiles, and they only do substitution reactions. When we go to weak bases and they become fair nucleophiles. So when we have weak bases and these fair nucleophiles, we're going to see a mixture of products. And then when we go to the weak bases, poor nucleophiles, think of the alcohol, water, and deprotonated acids, where they want to have a proton, but they're still weak bases because they're still fairly strong acids themselves. Whenever we get to that part, you gotta wait around for the carbocation. So you're gonna have a competition between SN1 and E1. But again, it's substrate dependent. So let's look at the substrates right here. Okay, so the first thing we wanna look at is methyl, okay? So in the methyl group here, because there is no beta carbon, there is no beta hydrogen. And if there is no beta hydrogen, it cannot do an elimination reaction. So everything but the weak base is going to give you an SN2 product, okay? Even your big bulky bases, because it is, the methyl group is small enough, the big bulky base can come in and do a slow SN2 reaction. Okay, now, once we switch over to primary, now we have a beta carbon. And with that beta carbon, we have a beta hydrogen. That means we can remove a beta hydrogen and elimination reactions become available to us, okay? So if we have a strong, if we have a good nucleophile, our SN2s are going to be major, okay? Good nucleophile, our SN2 is going to be major. Now, if we go to a strong, bulky base, the SN2 is now minor because it's so big, and our elimination product, our E2 product, becomes major. But notice when you have the strong bases or weak bases, you still get a little bit of that elimination, but the SN2 product is the major product for your primaries. Also notice that when we have our primary, we can't form a stable carbocation, and so therefore they don't work in the weak bases here. So methyls only do substitution reactions. Primaries, the better nucleophiles have the substitution products first. The poorer nucleophiles have the elimination first. The strong base but poor nucleophiles have the elimination first. Okay. Now let's go to secondary. Okay. Secondary, you typically have two choices of beta hydrogens. When you have your two choices of beta hydrogens and more steric demand, your elimination becomes your major product, okay? So you have twice as many beta hydrogens here as you had before, and you have steric demand, so you cannot form that SN2 product as readily, and therefore you get your E2 as your major, okay? So your elimination product. Notice when you have the big bulky base here, you only have E2, okay? It's too big, and the substrate is secondary. It's too big to get a substitution product, so it can't work. All right, but if we have a good nucleophile, it's not gonna beta eliminate. Your E2 product is gonna be your minor product because it's acting as a nucleophile first and acting as a weak base second. So our primary is gonna be our SN2 product. Okay, so notice that's different than our strong base. Even though it's small and a good nucleophile, the base is the primary. When we have a weak base, the substitution is primary. And then once we get to these poor nucleophiles, we can actually form a stable secondary carbocation, and we get a mixture of SN2, SN1, SNE1. Okay, because we have to, that one, because there's nothing there to act as a nucleophile, so we have to wait around for the carbocation. All right, when we move on to the tertiaries here, with a strong base, you only get elimination because it's sterically hindered. It cannot have it do a substitution reaction because of sterics, okay? So you only have E2. When you have a strong bulky base, again, you cannot have a substitution reaction because it's too, and so you have an E2. But now that you have a weak base, even though it's a good nucleophile, it's sterically hindered. It has to wait around for the carbocation, and therefore we have a mixture of the E1 and E2 because both mechanisms follow a carbocation first, and then what happens next, it can be either the elimination or the substitution product. Okay, so what I'm hoping you're seeing is I'm hoping you're seeing a pattern here, okay? Strong bases that are big and bulky are going to do elimination reactions except on methyls and primaries because of sterics, Okay. Weak bases are going to have substitution products be your major product because they're weakly basic. Strong bases can act as a nucleophile or a base. And once you get to your secondary, you have twice as many beta hydrogens, and therefore your elimination becomes the major product. And in tertiary, your elimination is the only product. Okay, so is this starting to make a little bit of sense now? Okay, so this is our kind of cheat sheet for this exercise. This is what we're going to be looking at and trying to make sure that we're seeing all these different things. But you're going to say, this doesn't help me. I go to the exam and I look at the equation and I just don't know where to start. Okay. Now I'm going to teach you how to strategize about where to start, what to look for, and how to down select to the correct mechanism based on what we know about these different reagents. Okay. So it doesn't have to be exactly in this order, but it really helps to know the different things you can look for. And when you know the different things you can look for, that can help you say, okay, it can't be that one, can't be that one, can't be that one, that's the only one I have left. So this is an order of elimination based on what you see in the system. So the first thing I always do is I like to have a great Lewis dot structure. And so you want your lone pairs on there because lone pairs can be can act as Lewis bases. Lone pairs can also have a negative charge. So you kind of want to know where those are. But you also want to know your polar bonds, okay? The polar bonds are the ones that are going to react. If you only have one polar bond on a molecule, that's where you're going to react. And so knowing which side is partially positive and which side is partially negative. For example, in the carbon iodine bond, we know iodine's more electronegative, so the carbon's going to be partially positive and the iodine's going to be partially negative. So that tells you that any nucleophile that comes in is going to be attacking the carbon, not the iodine. All right, so do that. Then you have to figure out which is the nucleophile and which is the electrophile, okay? Who has the electrons that are going to make that new sigma bond, okay? Once you determine what the nucleophile is and what the electrophile is, or Lewis acid and Lewis acid, then you'll know what's going to happen, what the leaving group is, okay? So that's going to help you identify that. The next thing we do is we classify it as primary, secondary, tertiary, methyl, allylic, benzylic, or vinyl or aryl. Why? Okay, well, by changing the nature of the leaving group, you have changed different mechanisms available to you, right? So you can, like for a primary, you're not going to have an E1 or an SN1. So you can eliminate those two immediately when you have a primary, okay? So things like that, knowing that you can do that. Now, the other thing to know is that aryl and vinyls don't undergo substitution reactions because they're not sp3 hybridized. So we can know if you have either one of those, no reaction can happen. Okay. The next thing we look at is what the nature of the nucleophile. Is it a strong or weak base? Okay. Is it a hindered or unhindered base? So is it big and strong? Is it small and weak? Is it, big and small? I'm sorry, strong and small. That will tell you whether or not it's going to favor elimination reactions. For example, strong and hindered is going to favor elimination reaction. Weak is going to favor an E1, E2 reaction. So you need to see, do you know if it's strong or not? So that's why knowing that table, knowing the different classifications in the table up above is important. Then you need to classify the attacking species as a good or poor nucleophile. If it's a weak base, good nucleophile, substitution SN2 is your primary mode. Okay. Now you look at the solvent. Okay. If you have a protic solvent and a secondary or tertiary electrophile, you can form a carbocation. You can only form carbocations in protic solvents. Okay, so if you have an aprotic solvent, acetone or something like that, you cannot form a carbocation. That eliminates E1 and SN1 as a possible mechanism. So then you're down selected to two different things, and all you have to do is look at size at that point and character. All right, what else do we look for? Okay, so by now you should have enough information to have eliminated some of the mechanisms. Okay, and then once you do that, you can think about, okay, if I have a competition between an elimination reaction and a substitution reaction, let's identify the hydrogens that we have, the beta hydrogens, and see where they can remote. Okay. If we can do that, we can look at, number one, doing our substitution reaction. Then we're going to draw another reaction where we do our elimination reaction. And we're going to eliminate the beta hydrogens based on whether it's a small base or a big base. And that's going to tell you the regiochemistry or the stereochemistry of the problem. If we're doing a substitution reaction and it's an SN2, we get inversion of stereochemistry. If we're doing an SN1 reaction, we're going to get a mixture of stereochemistry. So we need to pay attention to that. And then we want to look at, in the beta elimination, if it's small, we're going to form the more thermodynamically favored product, the Zaitsev product. If it's big and bulky, then we might form the Hoffman product, the less thermodynamically stable. And then the last thing to remember is no reaction is also an option, because if you have a weak, bulky base and a primary alkyl halide, nothing's going to happen. You cannot form a carbocation, nothing's going to happen. Okay, so don't take no reaction off. All right, so the next thing I'm going to do is I'm going to apply this. Okay, we're going to look at this reaction and apply some of these rules, but not necessarily all of them, and try to figure out what's happening. Okay, so just right here, we have a primary alkyl halide. All right. So primary alkyl halide tells us we're probably going to do an SN2 reaction, because that's the major thing we see in the SN2 reactions. So primary alkyl halide, but look, we have some E's as minor or major depending on the nature of the base. If it's a good nucleophile, we're going to get substitution reactions. If it's a strong, bulky base, we're going to get elimination reactions. But we have to do both of them to see what's going to happen. Okay, so, all right, so we have a primary. So we have those available to us. We have a deprotonated sulfur right here. This is polarizable, and this is not a strong base. We only have two strong bases that are small like this. We have the alkoxides and the hydroxides. So that means we have a good nucleophile and a weak base. And in addition, we have acetone, which means the E1, SN1 cannot happen, so we can eliminate those. So our only choices are SN2 and E2, okay? And because it's a good nucleophile and a poor base, we should be starting to think maybe substitution, but we'll see. Okay. So now let's figure out what the nucleophile is and what the electrophile is, okay? So if you just looked at it right here, you might not notice that the sulfur has a negative charge on it. So that's why putting the lone pairs on there is important, and the counterbalancing charge here. Now, on the alkyl halide, we don't have a full charge, but we do have a partially positive carbon and a partially negative bromine, telling us this is our nucleophile, this is our electrophile, and it's going to attack in exactly that place. That's the value of having those partial charges and charges there, okay? So let's see. We have acetone, so we can't do these. We have a good nucleophile, poor base, so this is going to be major, and this is going to be minor, okay? Because it's a weak base, the E2 product will be minor, okay? So now let's draw them, figure out what all the different products are. Okay. So the first thing we need to do is we need to do the substitution reaction. Okay. So in the substitution reaction, we're going to draw it as S there. But what would the elimination reaction be? The elimination reaction would be that, where we've taken off this alpha hydrogen and this bromine to give us a double bond. Now notice it's only a mono substitute, so we don't have to worry about stereochemistry of the alkene. That's the only one we can form. But of the two, our substitution product is going to be major, and this is going to be minor. So the other thing to think about is, would the reaction actually go? To know whether the reaction goes or not, we have to think about the base strength of the leaving group. Is the thing leaving a weaker base than the thing attacking? Okay, so in this case here, we have a sulfur compound, and so it has a pKa above 0. We have a bromine, and its conjugate acid would have a pKa that was negative, and therefore it's probably the weaker base, so the reaction will go, and it's going to go by an SN2 mechanism as the major product, and maybe a little bit of this. Minor. Okay, questions on that? See how you look at the substrate and see what is possible and then what is not possible, and you can down select. Once you get to the two possibles, your major and minor, then you draw out both reactions and look for things happening. Okay, let's do another example. Okay, so here, first of all, we have stereochemistry. So we need to think about, okay, what is our mechanism? And then what is the stereochemistry of the final product? Okay, so let's dig into this a little bit. So we have a secondary right here. So that gives us a couple different options, okay? When we have a secondary and we have a strong base and a good nucleophile in a protic solvent. So right now, before we do anything else, we have an SN1E1 possible, but because we have a strong base, our E1 and SN1 actually are eliminated. The protic solvent says it's available to us, but the strong base, strong nucleophile says no, the E1, SN1 will not work. We'd have to use something like water or methanol by itself. So now we know it's going to be an SN1, SN2, or an E2. So we only have two possible choices here. Now, one is going to give us a substitution product, so we're going to have stereochemistry over it. The other one's going to give an elimination product, and so we're going to have to figure out the most stable alkene. Because we have a small base, we're going to definitely form the more thermodynamic base. Let's do the same thing where we've identified our different attacking species. Of course, our carbon is the partially positive side, and this is our nucleophile that's going to come in as a nucleophile, or it's going to come in as a base. Okay, so those are our two possible mechanisms, an E2 or an SN2. Okay, so now because it's secondary, technically we can do an SN1 E1, but we have too strong a nucleophile and too strong a base, so that eliminated that. Methoxide is an unhindered strong base, so it can act as a nucleophile. Methoxide is a good nucleophile itself. And therefore, we need to think about what kind of E2 and SN2 products there might be. Okay. Okay. Now, when we talk about, okay, we have a strong base, we have a secondary halide. Okay. When you have that secondary halide, it is slightly sterically hindered compared with the primary alkyl halide. Now, once you see that it's slightly sterically hindered and you have an alpha proton here, right here, that means that in the secondary, system with a strong nucleophilic base, E2 will dominate. Okay, see, we're trying to get the substitution product is going to come in here, but the base product can come way out here. So because this is a secondary, E2 is going to be predominant. So E2 is going to be major, with SN2 being minor. Major. Okay. So let's draw the products. Okay. So if we draw the first product, the substitution product, right here, we're going to have attack by the nucleophile. It's kind of got to get in between these two methyl groups here, which is why it's the minor product. But what happens to the stereochemistry? An SN2 reaction, you are making and breaking a bond at the same time, meaning you get inversion of stereocenter. Okay. There should be an oxygen here, by the way. Okay. So it actually forms an ether. Okay. And it's the minor product because of the sterics. Okay. Now let's go and see which of the beta hydrogens we can attack using it as a base. Okay. So the first thing we can do is we can take the beta hydrogen. Because this is secondary, we can take a beta hydrogen off this outer methyl group here with 3 hydrogens on it. If we did that, we're going to get to an alkene, which is an E2 product. Okay, but that's not a very stable alkene. Okay, all right, let's go and try to get a hydrogen off the other one. So in one configuration where you have the 2 methyl groups on the same side, you can deprotonate here, form your double bond, and you're going to end up with this cis product. So it's an E2 product that's more thermodynamically stable than this product here, but I think we can do better. Okay, so if we rotate that bond around again so that these methyl groups are on opposite sides of each other and do that same reaction where we pulled off the beta hydrogen on the secondary carbon, we're going to end up with the trans product here. Okay, the trans product is the most thermodynamically favored product. Okay, so if we look at where they're going to be, we're going to have this as our major product. These two are going to be minor E2 products, and then our SN2 product will be also a minor product. Do you see why? Okay. Because we got to that secondary, it became sterically demanding. Sterically demanding was going to favor the elimination reaction. So let's go back to that chart and see if we're right. Let's see. Strong base, unhindered base on a secondary, yes. The E2 is major, and it's major because of sterics. Notice we had it as the minor in the primary, the major in the secondary, and only E2 in the tertiary. So we did it right. Okay. All right. Questions on that? Oops. Okay. So basically there were 3 possible ways to make E2 products, and we were able to form the most thermodynamically stable, which is the trans, and the bromide is a good leaving group, and it's a weaker base than the methoxide ion. So we know the reaction goes. All right, questions? All right, go ahead.
Yes, I do have one.
Okay, great.
On the exam, is it going to be like the top hat questions where the full given equation and like the product is given and we decide like which is the best product, or will we be having to actually do all of the charges and make our own product and decide if that was it?
You can do that on your own paper, but for the exam, it's going to be multiple choice, yes. Unfortunately, because of distance learning, we cannot draw. So it will be just a multiple choice. You pick the major product or the major and minor product out of the choices.
All right,
Okay.
thank you.
All right, so let me pull up the activity. Where is it? All right, let me pull up the activity and give you your instructions. I'm going to go ahead and stop sharing. And Finder. Downloads. Of course. All right, let me go ahead and go to Canvas and pull off Canvas. All right, so go ahead and pull that up, and I'm gonna, let me go ahead and screen share. Everybody can screen share, advanced options. All participants, multiple participants. There we go. All right, let me go ahead and pull up the activity for today. Activities, group activity. Should be released. All right, let me go ahead and share my screen again. There we go. Open. Okay, so this should be the thing. So this gives you the 2 slides that are the summary slides for chapters 6 and 7, okay? What to look for in your reaction, what the major products are going to be based on that. And so these are the 2 slides that we just went over. So that's going to be your guide, okay, for this exercise. I want you to work through the system together, you know, say, okay, where are the charges? What's the nucleophile? Is it good? Is it a good base, bad base? What's the substrate? Is it primary, secondary, or tertiary? Okay, so that's the important part. So then what I want you to do is I want you to look at the reaction here and say, okay, we have a methyl group here. We have a non-nucleophilic strong base. Okay, so we're not going to, this is a strong strong base. So we're not going to do an E2 reaction. We're not going to do it.
Screen?
Huh?
Are you sharing your screen? I can't see anything.
I'm sorry. I am sharing my screen. Okay, let me try again. All right, can you see the screen?
No.
No. Okay, let me.
Yes, that's the same. That is it, right? With the practice 1 example.
Yeah.
Okay, yeah, we can see it.
So it's just me.
All right, let me switch over to Adobe Acrobat. There we go.
Could just be me. I can like leave and come back and maybe it'll fix it.
Okay, let me just try in Acrobat here. All right, can you see my screen now?
No, I'm gonna restart Zoom.
Okay. All right. So I have the slide here for that and the slide here for this. This is what you're going to work through the process, each thing that you're going to have. And then here we start looking at stuff. Okay. What's the nucleophile? What's the electrophile? What's the nature of the carbon? Okay. Is it a primary, secondary, tertiary, or methyl? Okay. And then what is possible? Okay. Because we have a protic solvent, E1, E2, E1, SN1 is possible, but we have a strong base. So that eliminates E1 and SN1 as a product because we have a strong base here, okay? Now, so let's look at SN1 and SN2 and E2. So what would the SN2 product be? We would use this big bulky base. It's not a very good nucleophile, but the methyl group's small. So the methyl group's small and it can come in and attack and give us our substitution product here. Okay. Okay, let's look at our elimination product. First, we have to identify the beta hydrogens. There are no beta hydrogens on this compound because it's a methyl group. Because there are no beta hydrogens, we cannot do an elimination. Because we can't do an elimination, we don't have an E2 product. But if you draw both of them out and then X out the one that can't be, or in the case of most of these, I want you to figure out which one's the major product and which one's the minor product, okay? And so that would be this. So the things you would identify is there's a strong small base here. There's a primary alkyl halide. There's a protic solvent. What's going to happen? We have a big bulky base, a primary alkyl halide in a protic solvent. What's going to happen? We have a secondary. We have a secondary with a weak base. We have a tertiary with a strong base. So you're going to go through them each, talk it through, and figure out which of these different conditions it meets. Strong base, weak base, bulky base, small base, good nucleophile, bad nucleophile. And then figure out, based on the primary, secondary, or tertiary, what your product is. Draw your major and minor products and upload it to Canvas by midnight tonight. Okay? All right, I'm going to go ahead and stop share. Let's see how many people we have. We have 40 people. So I'm going to go to the breakout rooms here. We're going to do about let's do 8 breakout rooms, which gives you 4 to 5 people. And again, I'll stay here and I'll just call and ask me to come in, and I will come in and help get you on the right track. Okay. So I'm going to go ahead and create these and open all rooms. And there you go. Oh, I'm going to stop recording.